Hello YouTube, my name is Neil. This is MCAT study. I am studying for the MCATs and I was hoping to share it with you guys. Maybe you guys can benefit from it. To tell you the truth, this will help me stay accountable and stick to a schedule. So we're going to get started with the basics, physics, and math. I'm using this Kaplan book from 2017. We're going to jump right into the first chapter, which is Kinematics and Dynamics. Introduction. Professor once said biology is chemistry, chemistry is physics, physics is life. Not surprisingly, this was the claim of a physics professor. Walking into MCAT preparation, many students think of physics as the least applicable science to medicine, reflecting on calculus-heavy pre-medical classes. But even in the medical field, physics is all around us. When we treat patients at a rehab hospital, we often talk about motion, forces, and bone strength. An ophthalmologist may draw diagrams to help students better understand myopia and hyperopia. When we talk about mitochondria functioning as the batteries of the cell, we mean that fairly literally. This first chapter reviews the three systems of units encountered on the MCAT: MKS, meter, kilogram, second; CGS, centimeter, gram, second; and SI, International System of Units. We'll take a few moments to review the geometry of physics questions, especially vector mathematics. Next, we'll move into true physics content as we consider kinematics, the equations that deal with the motions of objects, and Newtonian mechanics and dynamics, the study of forces and their effects. All right. 1.1. Learning goals. After chapter 1.1, you will be able to recall the fundamental measurements and their units, order a given set of units that measure the same type of quantity from smallest to largest. Before we begin our discussion of motion, we must define a consistent vocabulary for our discussion of physics throughout this book. Physics relies on the language of mathematics to convey important descriptions and explanations of the world around us. Yet those numbers would themselves be meaningless or vague at best without the labels of units. Fundamental measurements. Over the years, various systems of units have been developed for specific purposes. Some of these systems are commonly used in everyday life, but rarely in science. The British imperial system, foot, pound, second, or FPS, is used commonly in the United States, but virtually nowhere else, not even in Britain. Basic units for length, weight, and time are the foot, the pound, and the second, respectively. Because weight and not mass is used, the British system later derived the slug as a unit of mass. MCAT rarely, if ever, utilizes FPS in passages or questions. The most common system of units in the metric system is the metric system, which is the basis for the SI units used on the MCAT. Depending on the context of a passage or question, the metric system may be given in meters, kilograms, and seconds, or centimeters, grams, and seconds. SI units include the MKS system as well as four other base units, as shown in Table 1. Length is meter, mass is kilogram, time is second, current is ampere, amount of a substance is moles, temperature is Kelvin, luminous intensity is the candela. In each measurement system, there are base units and derived units. Base units are the standard units around which the system itself is designed. Derived units, as the name implies, are created by associating base units with each other. For example, the Newton, a unit of force, is derived from kilograms, meters, and seconds. 1 Newton equals 1 kilogram meter per second squared. Table 1.2 contains examples of important derived units from each of the systems described above. Prefixes for metric units and conversions between metric and imperial units are discussed in Chapter 10 of MCAT Physics and Math Review. So we have mass is derived in FPS. Force is derived in SI units. So we saw that Newton is kilogram meter per second squared. Work is kilogram meter squared per second squared. And power is kilogram meter squared per seconds cubed. At the molecular, atomic, or subatomic level, different units may be given that are easier to work with at such a small scale. For example, length may be given in angstroms, or nanometers. Energy on the atomic scale can be expressed in electron volts, which represent the amount of energy gained by an electron accelerating through a potential difference of 1 volt. All right, we have our first concept checked. Before you move on, assess your understanding of the material with these questions. If the Newton is the product of kilograms and meters per second squared, what units comprise the pound? That is a good question. Can we figure that out? All right. What comprises the pound? Well, if work is foot-pounds, I have no idea. How do you do that? So what they did is they just used newtons over here. So a foot-pound is like a joule. So that's basically like a foot-pound. So I don't know, if we divide it by feet, do we get just pounds? That's what I'm going to go with. I'm going to go with if yeah, we're going to do that. If foot times pound equals a newton, which is kilogram times meter over second squared, and I'm going to divide this whole thing by feet. Put a feet over here, and I hope that that equals pounds. We'll find out. Number 2. Order the following units from smallest to largest: centimeter, angstrom, inch, mile, foot. I think we could do that. I think angstroms are small. Angstrom is less than centimeter. Let's just go cm, which is less than inch, which is less than a foot, which is less than a mile. All right, we'll see how we did on that. Vectors and scalars, 1.2. All right, so we're going to learn order of vector calculations, and we're going to calculate scalar or a vector as a product of two vectors using the right-hand rule when applicable. Vectors are numbers. They have magnitude and direction. Vector quantities include displacement, velocity, acceleration, and force. Scalars are numbers that have magnitude only and no direction. Scalar quantities include distance, speed, energy, pressure, and mass. The difference between a vector and a scalar quantity can be quite pronounced when there is a nonlinear path involved. For example, in the course of a year, the Earth travels a distance of roughly 940 million kilometers. However, because this is a circular path, the displacement of the Earth in 1 year is 0 kilometers. This difference between distance and displacement can be further illustrated with vector representations. Vectors may be represented by arrows. The direction of the arrow indicates the direction of the vector. The length of the arrow is usually proportional to the magnitude of the vector quantity. Common notations for a vector quantity are either an arrow or boldface. For example, the straight line path from here to there might be represented by a vector identified as A or A. The magnitude of the displacement between the two positions can be represented as A or A. Scalar quantities are generally represented with italics. The distance between 2 points could be represented by D. In this book and all books of the Kaplan MCAT review series, we would consistently use boldface to represent a vector quantity and italic to represent the magnitude of a vector or scalar quantity. Vector addition. The sum or difference of two or more vectors is called the resultant of the vectors. One way to find the sum or resultant of two vectors A and B is to place the tail of B at the tip of A without changing either the length or the direction of each arrow. In this tip-to-tail method, the length of the arrow must be proportional to the magnitude of the vectors. The vector sum A plus B is the vector joining the tail of A to the tip of B and pointing toward the tip of B. Vector addition is demonstrated in figure 1.2 below. So you have A plus B equals A plus B. A plus B plus C equals A plus B plus C. All right, another method for finding the resultant of several vectors involves breaking each vector into perpendicular components. In most cases, these components are horizontal and vertical, x and y components. However, in some instances, such as inclined planes, it may make more sense to define the components as parallel and perpendicular to some surface. Given any vector v, we can find x and y components of x and y by drawing a right angle with v as a hypotenuse, as shown in figure 1.3. So you could break it up into x and y components. If theta is the angle between v and the x component, then cosine of theta equals x over v, and sine of theta equals y over v. In other words, x equals cosine theta, y equals v sine theta. Oh, we're going to have to remember that. X is cosine, y is sine. Find the x and y components of the following vector. We could do this, I kind of have the answer right here. V equals 10 meters per second. Theta equals 30 degrees. So x equals 10 cosine 30. And cosine of 30 is root 3 over 2. I don't know how you're supposed to know that. We're going to have to review some trigonometry, because also the sine of 30 degrees is 1/2. I don't remember that. We're going to have to review this. We're going to have to go over some trigonometry. I can't believe they don't go over the trig with you. How are you supposed to know? How are you supposed to remember that cosine of 30 is root 3 over 2? Anyways. We're going to do this anyways. V equals 10. You don't have to do this. You can see it right here. If V is 10 meters per second, you're going to plug it into this. To get the x component, you're going to do 10 times the cosine of 30 degrees. And y, the y component will be 10 times sine of 30 degrees. Just have to know the sine of 30 degrees is 1/2. 10 divided by 2 is 5 meters per second. So that's the y component, and then the x component is 5 root 3. And we should be able to check that by doing like a little, our vector should equal the square root of 5 root 3 squared plus 5 squared, which is 25 over here, and this is 25 times 3, which is 75. 75 plus 25 is 100. The square root of that is 10. So at least we checked their work without being able to do it ourselves. All right. Well, that's something you remember that you can always check your work by plugging it back in, and you should get what you started with. And that's what they're trying to teach us here. Conversely, we know x and y. If we know x and y, we can find v, once again, by finding the root of the squares added together. So that's a Pythagorean theorem. Let's put that up there. Or not. Yeah, I do want to write that on there. Pythagorean Theorem. All right. So Pythagorean Theorem. X squared plus y squared equals, I don't know, z squared, v squared in this case. Or v equals the square root of x squared plus y squared. The angle of the resulting vector can also be calculated by knowing the inverse trigonometric functions discussed in Chapter 10. This inverse tangent calculation is beyond the scope of the MCAT. So maybe you don't need to know this for the MCAT. But you could also figure out the angle is the inverse tangent of y over x. What is the magnitude of the vector with the following components? X equals 3, y equals 4. We could do that. That's pretty easy. We know that v equals 3 squared plus 4 squared. Square root of that. 3 squared is 9 plus 16, which equals 25, which equals 5. And here you have, solution is 5. All right. The x component of a resultant vector is simply the sum of the x components of the vectors being added. Similarly, the y component of a resultant vector is simply the sum of the y components of the vectors being added. This is illustrated in figure 1.5. So you have vector 1, vector 2, y, the resultant y, and vector 3. You just add all the y's up, add all the x's up, and then that resultant vector is going to be all three of these vectors added up. So first split them up into x and y components. Add the x components to the x components to get rx, the resultant x vector, and then add all the y components to get ry, the resultant y vector. Find the magnitude of the resultant vector by this equation. Rx squared plus ry squared, square root. Find the direction using our little reverse inverse tangent function here. Vector subtraction. Subtracting one vector from another can be accomplished by adding a vector with equal magnitude but opposite direction to the first vector. This can be expressed mathematically by a minus b equals a plus negative b. Vector subtraction may also be performed on the component vectors first and then combined to create a final vector, as with the vector addition. The x component of the resultant vector is the difference of the x components of the vectors being subtracted. Similarly, the y component of the resultant vectors is the difference of the y components of the vectors being subtracted. Multiplication, all right. When a vector is multiplied by a scalar, its magnitude will change. Its direction will be either parallel or anti-parallel to its original direction. If a vector A is multiplied by a scalar value n, a new vector B is created such that B equals NA. To find the magnitude of the new vector, simply multiply the magnitude of A by the magnitude of n. Didn't I say n was a scalar? The absolute value of n. Okay. To determine the direction of vector B, we must look at the sign on n. If n is a positive number, then B and A are in the same direction. However, if n is a negative number, then B and A point in opposite directions. For example, if vector A is multiplied by a scalar plus 3, then the new vector B is 3 times as long and points in the same direction. If vector A is multiplied by the scalar negative 3, then B would still be 3 times as long but would point in the opposite direction. Multiplying vectors by other vectors. In some circumstances, we may want to multiply, we may want to be able to use two vector quantities to generate a third vector or a scalar by multiplication. To generate a scalar quantity like work, we multiply the magnitude of the two vectors of interest, force, and displacement, and the cosine of the angle between the two vectors. In vector calculus, this is called the dot product. So, let's erase some of this. We're going to keep that there, but we're going to move down a little bit. We're going to go dot product. You can see A dot B equals magnitude of A times the magnitude of B times the cosine of the angle between them. In contrast, when generating a third vector, like torque, we need to determine both its magnitude and direction. To do so, we multiply the magnitudes of the two vectors of interest, force and lever arm, and the sine of the angle between the two vectors. Once we have the magnitude, we use the right-hand rule to determine its direction. In vector calculus, this is called the cross product. So the cross product of A and B equals the magnitude of A times the magnitude of B times the sine of the angle between them. The resultant of a cross product will always be perpendicular to the plane created by the two vectors. Because MCAT is a two-dimensional test, this usually means that the vector of interest will be going into or out of the page. There are multiple versions of the right-hand rule that can be used to determine the direction of cross product resultant vectors. Shows one method considering a resultant C where C equals A times B. So right-hand rule, put your thumb in direction of A, you put your forefinger in direction of B, and the resultant will come out of your hand. Great. Right hand, use your right hand. Start by pointing your thumb in the direction. All right, that's what they just said. Note that you have learned a version of the right-hand rule that is different from what is described here. You may have. For example, some students learn to point the right index finger in the direction of A and the middle finger in the direction of B. When one holds the thumb perpendicular to these two fingers, it points in the direction of C. It makes no difference which version of the right-hand rule you use as long as you're comfortable with it and are skilled in its proper use. What are the magnitudes and directions of the resultant vectors from the following cross product? C equals A times B and D equals B times A. They should be the same because we're just taking magnitudes. Okay, so yeah, it should be the same either way, right? So A cross B will be magnitude of A, 3. The magnitude of B. How do we have to split up X and Y? No. Magnitude of A times the magnitude of B times the sine of the angle between them. Now, if the angle between them is 90 degrees, like in this case, sine of 90 is 1. I didn't remember that. Well, like I said, we're going to have to go over some trigonometry. Which just equals 3 times 4, 12. Wow. So once again, if you did this backwards, if you do B times A, kind of makes no difference because all you're doing is swapping these around. This is still going to be the same. And your answer is still going to be the same, I believe. All right. Oh, they also want to know whether it's into the page or out of the page. So in this case, A is in the X direction, Y is in the, or B is in the Y direction. So your resulting vector is going to be coming out of the page. In the other case, I guess B is your first, X is your second, and so the resulting vector is going into the page. So I guess these aren't exactly equivalent. These are not equivalent. See, it's saying C goes into the page, D goes out of the page. So I guess if our convention is that out of the page is positive, into the page would be negative. This would be a negative 12 in that case, wouldn't it? So why doesn't this result in a negative number? Oh, well, all right. Yeah, I don't know. It says over here, a key concept, A cross B does not equal B cross A. A dot B might, but A cross B does not. All right. MCAT concept check. Before you move on, assess your understanding of the material. When calculating the sum of vectors A and B, A plus B, we put the tail of B at the tip of A. What would be the effect of reversing this order? So if you go A and then B, if you go B and then A, you'll have a vector going in the opposite direction. When calculating the difference, should we write these down? Yeah, let's write them down so we can check them later. So 1.2, while up here this is 1.1. We're going to erase this. What's the effect of reversing order? Reversed resultant. Jeez. When calculating the difference of vectors A and B, A minus B, we invert B and put the tail of this new vector at the tip of A. What would be the effect of reversing the order? Also a reversed resultant. How is a scalar calculated from the product of two vectors? How is a vector calculated? So a scalar is the dot product. Scalar dot product. Vector cross product. Whatever. Cross product. True or false? If C equals A cross B, where A is directed toward the right side of the page and B is directed to the top of the page, then C is directed midway between A and B at a 45-degree angle. No, that's false. We know that a cross product will result in a vector that is perpendicular to both A and B. False. All right, we are moving on to 1.3, displacement and velocity. In chapter 1.3, you will blah, 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 and I'll consider basic geometry. It serves as the foundation of physics. Velocity and acceleration. Okay, displacement. An object in motion may experience a change in its position in space known as displacement, x or d. This is a vector quantity, and as such, has both magnitude and direction. The displacement vector connects in a straight line the object's initial position and its final position. Understand that displacement does not account for the actual path taken between the initial and the final positions. Only the net change in position from initial to final. Distance d traveled, on the other hand, considers a path taken and is a scalar quantity. So displacement is a vector. Distance is a scalar. What is the displacement of a man who walks 2 kilometers east, 2 kilometers north, 2 kilometers west, and then 2 kilometers south? While his distance traveled is 8 kilometers, his displacement is a vector quantity that represents the change in position. In this case, his displacement is 0 because the man ends up the same place he started, as shown below. All right. Velocity. As we mentioned earlier, velocity is a vector. Its magnitude is measured as the rate of change of displacement in a given unit of time. and its SI units are meters per second. The direction of the velocity vector is necessarily the same as the direction of the displacement vector, is necessarily the same as the direction of the displacement vector. Speed, v, is the rate of actual distance traveled in a given unit of time. The distinction is subtle, so let's examine this a little more carefully. The instantaneous speed of an object will always be equal to the magnitude of the object's instantaneous velocity, which is a measure of the average velocity as the change in time, delta t, approaches zero. So you can see how much the distance has changed in a second, and that'll be the average velocity. I mean, that'll be the total. All right, so the total distance traveled in an amount of time. You want the instantaneous. You want to take that limit to zero, that time interval. You want to make that as small as possible to get the instantaneous velocity at any moment. You know, it's calculus. Getting into calculus now. Where v is the instantaneous velocity, delta x is the change in position, and delta t is the change in time. As a measure of speed, instantaneous speed is a scalar number. Average speed will not necessarily always be equal to the magnitude of the average velocity. This is because average velocity is the ratio of the displacement vector over the change in time and is a vector, whereas average speed, which is scalar, is a ratio of the total distance traveled over the change in time. Average speed accounts for actual distance traveled, whereas average velocity does not. So velocity, all right, where were we? This is speed, this is velocity. Velocity is the vector, speed is scalar, speed is derived from, they're both derived from displacement, right, or distance. Anyways, consider the example given earlier regarding the Earth's orbit. In 1 year, the Earth travels roughly 940 million kilometers, but its displacement is 0. Distance, 9.4 times 10 to the 8th kilometers. Displacement, 0. The average speed is a measure of distance traveled in a given period of time. The average velocity is a measurement of displacement of an object over a given period of time. While the average speed of the Earth over a year is about 30 kilometers per second, its average velocity is again 0, because velocity is based on displacement. If displacement is 0, then velocity is still 0. Average velocity, not instantaneous velocity, but average velocity. Before you move on, assess your understanding of the materials with these questions. What is the relationship between instantaneous velocity and instantaneous speed? Between average velocity and average speed. So instantaneous velocity and instantaneous speed should be the same, right? The instantaneous speed of an object will equal the magnitude of the object's instantaneous velocity. So let's do 1.31. Instantaneous velocity. How do you write instantaneous velocity? I'm going to demark it VI. VI equals the magnitude of SI, which I'm calling instantaneous speed, even though that's not what they use. You're going to have to forgive me. If we really want to do this, we can go that and instantaneous velocity. I think I messed this up. Instantaneous speed is a magnitude of instantaneous velocity. Right? Did I do that right? Average speed and average velocity. So while instantaneous velocity is the magnitude, or instantaneous speed is the magnitude of instantaneous velocity, average speed does not equal the magnitude of average velocity. Alright, so I think that's good enough. True or false? Total distance traveled can never be less than the total displacement. I think this is true, because distance traveled cannot be negative, but displacement can be zero. Provide a definition for displacement or velocity in terms of the other variable. And plus you use absolute value, so it's never going to be less than. 3. Provide a definition for displacement or velocity in terms of the other variable. Displacement is, so if velocity is displacement over time, you could say displacement equals velocity times time. I think that'll do, right? It's not really a definition, but it's a relation. 1.4, forces and acceleration. Every change in velocity is motivated by a push or a pull, a force. In this section, we'll examine how forces interact with one another, as well as how acceleration results from those forces. Forces. Force is a vector quantity that is experienced as pushing or pulling on objects. Forces can exist between objects that are not even touching. While it is common for forces to be exerted by one object pushing on another, there are even more instances in which forces exist between objects nowhere near each other, such as gravity or electrostatic forces between point charges. The SI unit for force is the Newton, which is equivalent to 1 kilogram meter per second squared. All right. Gravity. When Newton observed apples falling out of trees, he was struck by the fact that they always fell perpendicular to the ground rather than sidewise or even away from the ground. Furthermore, Newton began to wonder about the farthest reaches of gravity. If the apple feels its attractive pull toward the earth, then what about the moon? Indeed, what Newton came to understand we call universal gravitation. Now, this is all grayed out, so I think that means that it might not. No, I think it's just poor printing. I think this page just didn't come in as dark. Gravity is an attractive force that is felt by all forms of matter. We usually think of gravity as acting on us to keep us from floating off of the Earth's surface or for holding the planets of our solar system in orbit. However, all objects exert gravitational forces on each other. There's a small but measurable force of gravity between you and this MCAT physics and math review book, the chair you're sitting on, and all the objects around you. Gravitational forces usually do not have much significance on a small scale because other forces tend to be much larger in magnitude. Only on the planetary level do gravitational forces really take on a significant value. The magnitude of the gravitational force between two objects is G, which is a universal gravitational constant, times the mass of one object times the mass of the other object divided by the distance between them squared. This equation is commonly tested in the context of proportionalities. For instance, the magnitude of the gravitational force is inversely related to the square of the distance. That is, if r is halved, then f will quadruple. So if this distance is halved, this will quadruple. The magnitude of the gravitational force is also directly related to the masses of the objects. That is, if m is tripled, then f will triple. An object twice as big has twice the gravity. An object at half the distance has 4 times the gravity. Find the gravitational force between an electron and a proton that are 10 to the negative 11 meters apart. Note, mass of a proton is 1.6, mass of an electron is 9.1, use Newton's law of gravitation. Let's try this out. We get to use some scientific notation here. And I think you could do this without a calculator. I wouldn't want to, but I guess you can. So this is not an exercise, it's just an example. We have a proton is 1.67 times 10 to the negative 27 kilograms. And the electron is 9.11 times 10 to the minus 31 kilograms. I think my F equals 1.67 times 10, oops, 10.7 times 9.11 times 10 to the negative 31, and we can't forget our G, which is 6.67. Now the unit for our gravitational constant is Newton meter squared over kilogram squared. Now the kg squared is going to cancel out with the two quantities, with the two masses of the two objects. And the meter squared is going to cancel out with the distance between the two objects. So all we're left with is newtons. So I'm going to avoid writing all that because we know it's going to cancel out in the end. This whole thing is going to be divided by the distance. We said they're 10 to the negative 11 apart, squared. That looks kind of beastly, huh? That looks big. It looks like they did some approximations. They went 20 over 3, 5 over 3. Are we going to do We're not going to do approximations, are we? We're just going to do it on a calculator, right? Do we have a calc? That did not work at all. Yeah, we're just going to do it on a calculator. 1.67. Oh my God, I got to turn this into scientific calculator. 1.67. E 27 times. Okay, I don't think that worked. Oh, this is hard. It's too difficult. All right, so we can just multiply the first numbers and add up the exponents. So we're going to do 1.67 times 1.11 times 6.67 equals, we got 101. What was that? 101.4. And then we're going to add up 11 minus 31 minus 27. That did not work. I'm going to have to find a new tablet to use. Yeah, I'm getting a different number than they got here. I didn't put a negative on here. Let's try it again. So then it'll just be 11 plus 31 plus. I think it was 69 first. Did I do that right? Let's do that again. $69. Why are they getting 67? 11, 31, 27. 11 plus 31 plus 27 is 69 over 22. So how does it become? Oh, because there's an extra 100 there. It's next to 10 there. Yeah, I'm getting a different number than them. Should we do this calculation again? 1.67 times 9.11 times 6.67 equals 101. So how does 100 to the negative 69th become 100 to the negative 67? It should be 68. Right, because they have 10. I don't know, they got a different number than I'm getting. I think they made a mistake. I think they're one off. If I move this decimal point over, make it and round it off to 10 like they got it, this becomes an 8 because I took a 10 out of it, not a 7. I don't know how they got 10 to the negative 67. It should be 10 to the negative 68. I don't know. Maybe I'm making a mistake. I'll go back and double check this. So they get some answer. They get negative 45. I would have gotten negative 6 or 40. Yeah, I would have gotten negative 46. We'll see. We'll have to hash that out. We'll have to circle back to this. Let's mark that off. Let me take another look at that. All right, let's get back to reading. Maybe they have an explanation for that at the end of the chapter. All right, friction is a type of force that opposes the movement of objects. Unlike other kinds of forces such as gravity or electromagnetic force, which can cause objects either to speed up or slow down, friction forces always oppose an object's motion and can cause it to slow down or become stationary. There are two types of friction, static and kinetic. Static friction, Fs, exists between a stationary object and the surface upon which it rests. The equation that describes the magnitude of static friction is 0 is less than or equal to static friction, which is less than or equal to mu n, where mu is the coefficient of static friction and n is the magnitude of the normal force. The coefficient of static friction is a unitless quantity that is dependent on the two materials in contact. The normal force is the component of the force between the two objects in contact that is perpendicular to the plane of contact between the object and the surface upon which it rests. Note the less than or equal to sign in the equation. These signify that there is a range of possible values for static friction. The minimum, of course, is 0. This would be the case if an object were resting on a surface with no applied force. The maximum value of static friction can be calculated from the right side of the previous equation. One should not assume that objects that are stationary are experiencing a maximal static force of friction. Consider trying to push a heavy piece of luggage. When a 25 Newton force is applied, the bag does not move. When a 50 Newton force is applied, the bag still does not move. 100 Newton force is applied, the bag slides a meter or so and slows to a rest. This setup implies that the maximal value of static friction is somewhere between 50 and 100. Any applied force less than this threshold will not be sufficient to move the bag, as there will be an equal but opposite force of static friction opposing the bag's motion. Kinetic friction exists between a sliding object and the surface over which the object slides. Sometimes students misidentify the presence of kinetic friction. A wheel, for example, that is rolling along a road does not experience kinetic friction because the tire is not actually sliding against the pavement. The tire maintains an instantaneous point of static contact with the road and therefore experiences static friction. Only when the tire begins to slide on, say, an icy path will kinetic friction come into play. Anytime two surfaces slide against each other, kinetic friction will be present, and its magnitude can be measured according to this equation. F of k equals mu of k, n. It's not that different from here, but equal to rather than less than or equal to. Where mu k is the coefficient of kinetic friction and n is the normal force, there are two important distinctions between this equation for kinetic friction and the previous equation for static friction. First, the kinetic friction equation has an equal sign. This means that kinetic friction will have a constant value for any given combination of a coefficient of kinetic friction and a normal force. It does not matter how much surface area is in contact or even the velocity of the sliding object. Second, the two equations have a different coefficient of friction. The value of mu s is always larger than the value of uk. Let's remember that. Mu s is always larger than mu k. Therefore, the maximum value for static friction will always be greater than the constant value for kinetic friction. Objects will stick until they start moving and then will slide more easily over one another. As previously mentioned in the discussion of static friction, pay close attention to the conditions set in the MCAT passage. Does it say that friction can be assumed to be negligible, or does it provide the coefficient of friction values, which will most likely need to be used in a calculation of friction? Friction will be incorporated into our examination of translational equilibrium later in this chapter. Mass and weight. Mass and weight are not the same. Mass is a measure of a body's inertia, the amount of matter in the object. Mass is a scalar quantity and as such has magnitude only. The SI unit for mass is kilogram and is independent of gravity. 1 kilogram of material on Earth will have the same mass as 1 kilogram of material on the moon. Weight, on the other hand, is a measure of gravitational force, usually that of the Earth, on an object. Because weight is a force, it is a vector quantity with the units of newtons. While mass and weight are not synonymous, they are related by the equation F equals mg, where F is the weight of the object, m is the mass, and g is the acceleration due to gravity, usually 9.8 meters per second. Negative 9.8 meters per second. The weight of an object can be thought of as being applied to a single point in that object called the center of mass or gravity. The MCAT will not directly test your ability to determine center of mass. However, such a calculation may be an important step in a problem with a larger focus of Newtonian mechanics. To illustrate the concept in calculation, consider a tennis racket that has been thrown into the air. Each part of the racket moves in its own path, so it's not possible to represent the motion of the whole racket as a single particle. I'm just going to write down F equals MA/mg. However, one point within the racket moves in a particular parabolic path, very similar to the flight of a ball. It is this point within the racket that is known as the center of mass. So even though this part of the racket and this part of the racket, the middle of the racket is the center of mass. Okay. For a system in which particles are distributed in all three dimensions, the center of mass is defined by the three coordinates x, y, z, where m1, m2, and m3 are the three sample masses, and x, y, z are coordinates. The center of gravity is related and corresponds to the single point at which you can conceptualize gravity acting on an object. Only for a homogeneous body with symmetrical shape and uniform density should one expect the center of gravity to be located at its geometric center. For example, we can approximate the center of gravity for a metal ball at the geometric center of the sphere. The same cannot be said, however, for a human body, television, or an asymmetrical, non-uniform object. Acceleration is the rate of change of velocity that an object experiences as a result of some applied force. Acceleration, like velocity, is a vector quantity and is measured in SI units of meters per second squared. Acceleration in the direction opposite the initial velocity may be called deceleration. Average acceleration is defined as rate of change of velocity over the rate of change of time, where A is the average acceleration, V is the change in velocity, and T is the change in time. Instantaneous acceleration is defined as the average acceleration as delta T approaches 0. On a graph of velocity versus time, the tangent to the graph at any time t, which corresponds to the slope of the graph at any time, indicates the instantaneous acceleration. If the slope is positive, the acceleration is positive and is in the direction of the velocity. If the slope is negative, acceleration is negative, deceleration, and is in the opposite direction of velocity. Before you move on, assess your understanding of material. 1.4. When calculating frictional forces, how is directionality assigned? When calculating frictional forces, how is directionality assigned? Well, I guess it's perpendicular to the surface. So if you're at an angle, then, wow, this whole section of my pad does not work. So if you're at an angle, instead of doing friction, like your normal force, while your normal force is down, we're going to break it up into x and y components, I guess. What are you supposed to do? You're supposed to find the normal force in the direction of, so if something's sliding down, then the friction is going to be in that direction, and the normal force is going to be down. You're going to be going perpendicular to the force, or to the plane that you're talking about. So directionality is assigned relative to surface, i.e. perpendicular. 1, 2 is going to be when no force is being applied, the velocity must be. When no force is applied, that doesn't mean that its velocity is 0. That means acceleration is 0. When no force is applied, or are they talking? The velocity must be constant. No acceleration. True or false? The Earth creates a large force on you, a larger force on you than you create on the Earth. That's false. We create an equal amount of force on each other. It's just that amount of force affects our small bodies more than the Earth's large body. Name two forces in addition to mechanical manipulation, pushing or pulling forces created by contact with an object. Name two forces in addition to mechanical manipulation. Name two forces? So the normal force is... Oh, other than contact. So gravity is one, and I guess electromagnetic force. Yeah, that'll do. Let's see, 1.5. How long is this chapter? Oh, I think we're almost there. 1.7. Two more sections. All right, Newton's laws. Now that we have a clear understanding of force, mass, and acceleration, let's examine how they relate to each other. While it is unlikely that Newton discovered gravity by having an apple on his head, he did record that he was indeed inspired by watching apples fall from trees. His observations about objects in motion and at rest are the basis for the branch of physics that we now know as mechanics. Newton's laws, which are expressed as equations, concisely describe the effects of forces have on objects that have mass. F equals ma, where F is the net force, m is the mass, and a is the acceleration. So it resembles this, doesn't it? In this case, the acceleration was just the acceleration due to gravity. We'll write it again. F equals ma. Acceleration, mass, force. A body either at rest or in motion with constant velocity will remain that way unless a net force acts upon it. This is known as the Law of Inertia. Newton's first law ought to be thought of as a special case of his second law, which is described next. So the first law is inertia, which is a special case of the second law. Okay, so the first law is that this equals 0 for an object at rest. For an object in motion, the second law, I guess it won't be equal to 0. For an object in motion, an object of mass m will accelerate when the vector sum of the forces results in some non-zero resultant force vector. No acceleration will occur when the vector sum of the forces results in a cancellation of those forces. Note that the net force and the acceleration vectors necessarily point in the same direction. This law is known as the law of action and reaction. So the third law, to every action there is an equal and opposite reaction. FAB equals minus FBA. The force that A puts on B is equal and opposite to the force that B puts on A. So like you and the Earth put equal and opposite force on each other. More formally, the law states that for every force exerted on object yeah, I guess that's what they just said. When you hit your hand against the desk, your hand exerts a force on the desk. Simultaneously, the desk exerts a force of equal magnitude in the opposite direction on your hand. Physical contact is not necessary, so this works through gravitation, like you and the Earth, or the Earth and the Moon. In your own words, provide a description of Newton's laws of motion. So, in our own words, the first one was that when F equals ma equals 0, so object at rest, no force or acceleration for motion, force equals mass times acceleration. And we write this as A is applying a force to B. That implies that B also has an equal and opposite force on A. Oh, that's good enough. You get it. Motion with constant acceleration. Objects can undergo only two types of motion. That which is constant with no acceleration, or that which is changing with acceleration. If an object's motion is changing, as indicated by a change in velocity, then the object is experiencing acceleration. And that acceleration may be constant or itself changing. A moving object that experiences constant acceleration presents a relatively simple case for analysis. The MCAT tends to restrict kinematics problems to those that involve motion with constant acceleration. Yeah, I can imagine that'd be easier. Linear motion. In linear motion, the object's velocity and acceleration are along the line of motion. So the pathway of the moving object continues along a straight line. Linear motion does not need to be limited to vertical or horizontal paths. The inclined surface of a ramp will provide a path for linear motion at some angle on the MCAT. The most common presentations of linear motion problems involve objects such as balls being dropped to the ground from some starting height. Following objects exhibit linear motion with constant acceleration. This one-dimensional motion can be fully described by the following equations. V equals initial velocity plus acceleration times time. Distance equals initial velocity times time plus acceleration times time squared over 2. V squared is acceleration equals initial velocity squared plus 2 times acceleration times distance. So this is moving this equation around. V squared is acceleration, right? No, V squared is not. X equals the derivative of velocity is acceleration. X equals Vt. Distance traveled equals velocity times time. V naught is the initial velocity. The bar is the average velocity, and t is time. When the motion is vertical, we often use y instead of x for displacement. To demonstrate the typical setup of a kinematics problem, we will consider an object falling through the air. For now, we will assume air resistance to be negligible, meaning that the only force acting on the object would be the gravitational force causing it to fall. Consequently, the object would fall with constant acceleration due to gravity, negative 9.8. It would not reach terminal velocity, that is free fall, under these conditions, which are typical for test A. We could analyze the fall using the relative kinematics equation. A ball is thrown vertically up into the air from a window ledge 30 meters above the ground with an initial velocity of 10 meters per second. Should we draw this? Let's get an example here. It starts 30 meters above the ground. Then the ball goes up at a velocity of 10 meters per second. Find the velocity and position of the ball after 2 seconds. So 10 meters per second. 2 seconds is going to be 20 meters up, right? But it wants the velocity and position of the ball after 2 seconds. So there's so there's acceleration. There's a negative 9.8 acceleration. So I want to say that, okay, so if it's got a velocity, then it doesn't matter that acceleration's down. After 2 seconds, it'll climb 20 meters. plus the original 30. This drawing is bad. Let's make this long. Started at 30 and went up an additional 20, total of 50. Find the distance and time. Oh, the velocity. Well, after 1 second, won't it decelerate? Oh, so after 2 seconds, it'll come back to the same spot because it'll have decelerated. So I changed my mind about this. In 1 second, it'll go up 10 meters, but acceleration will decrease its velocity down to 0. And then in the second, it'll come back down to the same spot. So its velocity will be going down at 10 meters per second, and its position will be at 30 meters. At 30 meters. Find the distance and time at which the ball reaches its maximum height above the window ledge. The maximum is 40 at time of 1 second in. Remember, the velocity and acceleration are vector quantities for this question. Let's call the ball's initial position y0. If we consider up to be positive, then the initial velocity is positive 10 meters per second, and the acceleration is negative 9.8. Note that g is negative because it's oriented downward. Velocity after 2 seconds can be found using equation 1. V equals v naught plus at. So 10 plus negative 9.8 times 2 seconds. I just round that up to 10, but there's actually a little bit of difference. There's a negative 9.6 meters. After 2 seconds, the position of the ball is found using equation y equals v naught t plus at squared over 2. 10 times 2 plus negative 9.8 times 2 over 2. 0.4 meters above the ledge. I mean, we're pretty close. We said 0. We rounded 9.8 to 10. We did the right thing. When the ball is at its maximum height, the velocity, which has been decreased on its way up, is now 0. We can find the maximum height of the ball reaches this equation. 10 plus 2 minus 9.8. 19.6 equals 100. So around 5 meters, actual 5.1 meters. The time at which the ball reaches its maximum height can be found at 1 second. So we got that right. We got 1 second. We said it was going to be 40 meters up. I mean, it's decelerating all that while. Yeah, it's not really going to climb 10 meters. We should have used this equation here. V squared equals v naught squared plus 2ay. So the velocity, so when the velocity is 0, and its starting velocity was 10, plus 2, its acceleration is negative 10. We want to know what height it reaches. So we have a negative 20y equals 100. And then divide that by 20, and you get y equals, 5 meters over 30. Still at 1 second. But yeah. The acceleration is changing, so we can't assume that it goes 10 meters in that second. It's slowing down. It only goes 5 of those meters. All right, so we learned some there. This equation here is key. Also, the way they use this equation, I just winged it. I just assumed that traveling at 10 meters a second, whatever. Because its initial is 10 upwards, it's accelerating 10 downwards, so after 1 second, those will kind of cancel out. We could have used this equation. We kind of cheated on that. I kind of cheated. All right, let's move on. Let's now consider what happens when air resistance is not negligible. Air resistance, like friction, opposes the motion of an object. Its value increases as the speed of the object increases. Therefore, an object in free fall will experience a growing drag force as the magnitude of its velocity increases. Eventually, this drag force will be equal in magnitude to the weight of the object, and the object will fall with constant velocity according to Newton's first law. This velocity is called the terminal velocity. So it's when the resistance, the drag due to resistance, equals the acceleration due to gravity. So the acceleration is 9.8. When the drag forces upwards on an object, so the faster you go, the more drag. At some speed, the drag force will equal 9.8, and then you'll stop accelerating downward and you'll just free fall. I guess that's what skydivers do. Kind of feels like flying around. All right, projectile motion is motion that follows a path along two dimensions. The velocity and acceleration in the two directions, usually horizontal and vertical, are independent of each other and must accordingly be analyzed separately. Objects in projectile motion on Earth, such as cannonballs, baseballs, or bullets, experience the force and acceleration of gravity only in the vertical direction along the y-axis. That means that Vy will change at the rate of g plus Vx will remain constant. But Vx will remain constant. In fact, on the MCAT, you will generally be able to assume that the horizontal velocity will be constant because we usually assume that air resistance is negligible and therefore no measurable force is acting along the axis. A projectile, all right, let's do another example. I'm going to keep this example up because we might come back to it. A projectile is fired from ground level with an instant initial velocity of 50 meters per second and an initial angle of 37 degrees. Assuming g equals 10, find the following. Note, sine of 37, so they give us sine of 37 equals 0.6. And cosine 0.8. Thanks, that's handy. And they got a little diagram. We have a ball. We have an angle of 37 degrees. And then we have a velocity. Initial velocity equal to 50. So we need to find the projectile's total time in flight and the total horizontal distance traveled. So I'm going to break this up into x and y components. You remember x equals, I think x was cosine. Was x sine or was x cosine? How do we do that? X equals. I think x was cosine, right? Should we just go back and look at that real quick? Yeah. X equals cosine, y equals sine. So cosine theta, 0.8 times initial velocity. times 0.8 is going to be 50 times 0.6, which equals, should we do that on our calculator? 40, 30. So it's x is 40. It's y is 30. I guess we could have figured that out. 3 times 3 squared plus 4 squared equals 5 squared. All right. So we have the components, the projectile's total time in flight. So we need to find time. So it's got an initial velocity of 30 up. So initial velocity of 30. And we want to know how long till it comes down to 0, till y is 0. Because first y starts out 0, it goes up in the air, and then it comes back down. So when y is 0, at some time, plus the acceleration we know is -10. So we have to solve for t in this little quadratic equation here. Fun. They don't have a negative. That won't make a difference, right? We'll just have a negative in our answer and they won't. 10 divided by 2 is 5. 30t plus 5t squared. So where did this negative come from? They just added it in. Because there's no negative up here. They're just winging it just like we are. Yeah, that's a negative, right? All right. Do you remember how to do these? Oh, this one we don't actually have to go quadratic. This equals 5t squared equals 30t. Just take the 5t squared to the other side. Oh, we do have to. Oh no, then divide by 5. And yeah, I'm terrible at math. T squared equals 6t. So t can be 0 or 6. How are you supposed to do that again? Isn't it easier to factor it or something? Well, 0 works and 6 works because 6 times 6 equals 6 times 6. So it'll reach the ground at 6 seconds. And the distance traveled. So in 6 seconds, going to the right at 40 meters per second. Now that speed doesn't change due to gravity because that's horizontal. It's not affected by gravity. So that's a constant 40 meters per second for 6 seconds. So I think you can just go 40. Times 6 equals 240. that what they did? Yeah, they got the x component, and this is all just 0 because there's no acceleration. So it's just 40 times 6, you get 240. Second half was easier. First half takes a little bit of math. You have to remember your math. You have to remember how to do these things. For a math review, we're not really doing the basics of math, are we? We just jumped into physics. All right, inclined planes are another example of motion in 2 dimensions. When working with an inclined plane question, it is often best to divide force vectors into components that are parallel and perpendicular to the plane. Most often, gravity must be split into components for these calculations. These components can be defined as Fg parallel, Fg perpendicular. Force of gravity, parallel and perpendicular, and we use sine and cosines to do that. All right, we got another example. We got a 5-kilogram block slides down a frictionless incline at 30 degrees. Find the normal force and acceleration of the block. Note, sine of 30 is 0.5, sine of 60 is 0.86, cosine of 30 is 0.86, cosine of 60 is 0.5. Normal force and acceleration. So we have an incline. We have a block. There's a force of gravity going that way. And we want to break that up into a perpendicular and a parallel component. How do we do that? To a parallel and perpendicular component. I want one going this way. Where's the right angle? I want this component and this component. All right, so I just have to make different triangles for each component, huh? All right, whatever. So how do we know which one is the sine and which one is the cosine? I thought x is cosine. So the parallel component I thought would be cosine. The perpendicular component is cosine. Parallel to the plane. Sine is parallel to the plane. Cosine is perpendicular to the plane. Okay, if you say so. Where are our numbers at? 5 kg. And we have 30 degrees. And we know that sine of 30 is 0.5. cosine of 30 .866 60 0.66 0.866 cosine of 60 equals 0.5. So F perpendicular is going to equal 5 times, can we go 10? Or do we have to go 9.8? We're just going to go 10 times sine of 30, and F perpendicular equals 5 times cosine 30. And it's going to be 50 divided by 2, 25. It's going to be 50 times 0.86. 43. Now let's go through so that's the acceleration. The normal force so let's see what they did here. They did F perpendicular equals 5 times 9.8 cosine 30, which is about 50. What? Oh yeah, this is the cosine one. 43.3. Acceleration can then be determined in the parallel direction because the only force in this dimension is the parallel component of the force of gravity. It is the net force. So F equals ma mg sine theta. So they did 9.8 sine theta. Oh, to find the acceleration. So this is the force. To turn this into acceleration, basically you're going to divide by the mass. So here, mass is 5. 25 divided by 5. See it. F equals ma. Mass is 5. Force is 25. A equals 5. All right. Circular motion. Circular motion occurs when forces cause an object to move in a circular pathway. Upon completion of one cycle, the displacement of the object is 0. All that the MCAT focuses on uniform circular motion, in which case the speed of the object is constant. Recognize that there is also non-uniform circular motion. In uniform circular motion, the instantaneous velocity is always tangent to the circular path. What this means is that the object moving in the circular path has a tendency, inertia, to break out of a circular path. It wants to go straight, move in a linear direction along the tangent. It is kept from doing so by a centripetal force, which always points radially inwards. In all circular motion, we can resolve the forces into radial and tangential components. In uniform circular motion, the tangential force is 0 because there is no change in the speed of the object. As a force, the centripetal force generates centripetal acceleration. Remember from the discussion of Newton's laws that both force and acceleration are vectors, and the acceleration is always in the same direction as the net force. Thus, it is this acceleration generated by the centripetal force that keeps an object in its circular path. When the centripetal force is no longer acting on the object, it will simply exit the circular path and assume a path tangential to the circle at that point. The equation that describes circular motion is Fc equals mv squared over r, where F is the magnitude of the centripetal force, m is the mass, v is the speed, and r is the radius of the circular path. Note that the centripetal force can be caused by tension, gravity, electrostatic forces, or other forces. 1.6. Before you move on, assess how do the forces acting in free fall and projectile motion differ? Free fall and projectile motion. Free fall, I guess, has no x component. They don't. My answer is they don't. Well, I guess y component is the same. X is different. At what angle of launch is a projectile going to have the greatest horizontal displacement? What angle will result in the greatest vertical displacement, assuming a level surface? At what angle is a projectile going to have the greatest horizontal displacement? 45 degrees. Greatest vertical displacement? So you can't achieve vertical displacement. Horizontal, 45 degrees. Vertical, relevant. What is the equation for centripetal acceleration? That was F equals mv squared. Oh, that's for force. So if F equals ma, so just the acceleration part is going to be basically this divided by m. Equals v squared over r. All right. We're at the last section of this chapter. And then we got a little concept checked. Practice questions is what we have. The concept checks, we're going to go through our answers with the questions at the end. Answers to concept checks. Did they not already give us the answers? They didn't, huh? All right, let's get through this last section. Mechanical equilibrium. So far, we've been paying attention to kinematics in similar cases of linear and projectile motion. However, many times The MCAT will require us to eliminate acceleration or otherwise maintain a system in equilibrium. To accomplish this, we must be familiar with analyzing forces, especially with free body diagrams, as well as with the special conditions for translational and rotational equilibrium. The study of forces and torques is called dynamics. Free body diagrams. While we all have an intuitive sense of forces and their effects in everyday life, students often struggle to represent them diagrammatically. Drawing free body diagrams takes some practice, but will be a valuable tool on the MCAT. On test day, make sure to draw a free body diagram for any problem in which you must perform calculations on forces. Example. Great. 3 people are pulling on ropes tied to a tire with forces of 100 newtons, 125 newtons, 125 newtons. Find the magnitude and direction of the resultant force. Note, sine of 30 is 0.5, cosine of 30 is 0.86, sine of 37 is 0.6, cosine of 37 is 0.8. So, 125 newtons that way. Find the magnitude and direction of the resultant force. So there's 125 this way, 125 that way, and then 100 that way. So the 125 in that direction, at 37 degrees, we're going to break that up into x and y. So x with sine. X component is, yes, the vector 125 times cosine 37, 125 sine 37 is going to be the x and y components. So we learned that cosine of 37 is 0.8. So 120. Sine of 37 is 0.6. $80 and 75. Was that right? Oh, 100. Oops. So these are the x and y components of that first guy pulling. Now this other guy is similarly going to be 100. We can skip that. 100 times 0.8, 100 times 0.6. A little easier, 80 and 60. It's in the x direction and the y direction. This x is different than this x, though. This is negative, and that's positive. So we'll put a negative over here. But they're both in the positive y direction, while this guy is 125 in the negative y direction. So, 100 to the left, 80 to the right. It's going to go 20 to the left. And then the y is in the same direction for both these guys. 75 plus 60. Right? Yeah. 135. and 125. So that's going to be 135 up minus 125 down. 10 up. So it's going to go so we could turn that back into like an angle too, I guess. 10 up, 20 that way. 10 up, 20 that way. Let's put this over here. Resulting vector can be 4 plus 1, 5, square root of 5. Oops. Let's see. How do we find the last step? Why are they getting different numbers than this? What are we doing here? Cosine 30, oh, cosine 37 and 30. I use the same cosines, but it's not 37, it's 30, not 37. I messed up here. Let's do this again. 100 times cosine of 30 and sine of 30. Cosine of 30 is 0.86. This is going to be 86.6. Sine of 30 is 0.5. It's going to be 50. Let's add these back up. 86.6 minus 100 equals 13.4. I think that's what they got. I think I remember seeing that. And then we have 75 plus 50. 125 in the up direction, 125 in the down direction. They cancel out. 50 plus 75 minus 125 equals 0. No y movement, but an x movement. So all it'll do is go to the left at 13.4 newtons. All right, little hiccup, but we learned something. We worked through that. Don't mess up your cosines and sines. All right, let's move on. Translational equilibrium. Translational motion occurs when forces cause an object to move without any rotation. The simplest pathways may be linear, such as when a child slides down a snowy hill on a sled, or parabolic, as in the case of a cannonball shot out of a cannon. Any problem regarding translational motion in the chemical and physical foundations of biological systems section can be solved using free body diagrams and Newton's 3 laws. Equilibrium conditions. Translational equilibrium exists only when the vector sum of all of the forces acting on an object is 0. This is called the first condition of equilibrium, and it is merely a reiteration of Newton's first law. Remember that when the resultant force upon an object is 0, the object will not accelerate. That may mean that the object is stationary, but it could also just as well mean that the object is moving with a constant non-zero velocity. Thus, an object experiencing translational equilibrium will have a constant velocity, both a constant speed, which could be 0 or a non-zero value, and a constant direction. Two blocks are in static equilibrium, as shown below. Got a 15 kilogram mass up here. What's the mass of this? The block A has a mass of 15 kilograms, and the coefficient of static friction between block A and the surface is 0.2. What is the maximum mass of block B? Well, if it's not moving, if it's in equilibrium, it's got to be the same, right? So 15 times 0.2 is 3. The force I guess Kind of a simple problem, because the force of friction you calculate to be 15 times, or the mass times the coefficient of friction, 15 times 0.23. Rotational equilibrium. Rotational motion occurs when forces are applied against an object in such a way as to cause the object to rotate around a fixed pivot point, also known as the fulcrum. Application of force at some distance from the fulcrum generates torque, or the moment of force. The distance between the applied force and the fulcrum is termed the lever arm. It is the torque that generates rotational motion, not the mere application of the force itself. This is because torque depends not only on the magnitude of the force, but also on the length of the lever arm and the angle at which the force is applied. The equation for torque is a cross product. Torque equals the length of the arm times the force applied, the magnitude of the force. And that is, the cross product. So RF sine theta. Let's write that down. Tau equals R cross F, or RF sine theta, where R is, alright. Equilibrium conditions. Rotational equilibrium exists only when the vector sum of all the torques acting on an object is zero. This is called the second condition of equilibrium. Torques that generate clockwise rotation are considered negative. Torques that generate counterclockwise rotation is positive. Okay. Thus, in rotational equilibrium, it must be that all of the positive torques exactly cancel out all the negative torques, similar to the behavior defined by translational equilibrium. There are two possibilities of motion in the case of rotational equilibrium. Either the object is not rotating at all, that is, it's stationary, or it's rotating with a constant angular velocity. The MCAT almost always takes rotational equilibrium to mean that the object is not rotating at all. A seesaw with a mass of 5 kilograms has one block of mass, 10 kilograms, 2 meters, to the left of the fulcrum, and another block 0.5 meters to the right of the fulcrum, as shown below. The seesaw is in equilibrium. Find the mass of block 2 and the force exerted by the fulcrum. Okay. So, here theta is just 90 degrees. We can ignore theta. Basically, this so R times mass times gravity over here equals R times mass times gravity over here. Or just Rm equals Rm. So over here, 10 times 2 meters. Times 2 meters, which is the distance here. And this is a seesaw with a mass of 5 is one block of mass 10. So why does it matter what the mass of the seesaw is? That's just there to confuse you. Basically, 10 times that distance has to equal this distance times the mass that we're looking for. And since this divided by 0.5 is this divided by 0.5, which is that times 2, so it's just 40. A mass at half the distance. Is that right? That's what they did. 40. To find the normal force exerted by the fulcrum, consider that the seesaw is not only in rotational equilibrium, but also in translational equilibrium. Therefore, the combined weight of the seesaw and blocks is equal in magnitude to the normal force pointing up. So the normal force on the fulcrum, so it's not rotating, but it's got 40 kilograms, 10 kilograms, and another 5. So 40, 50, 55 kilograms on that fulcrum. So basically we're just going to go 55 kilograms times the force of gravity, 9.8, or we'll go with 10. Newtons. 550 newtons. Before you move on, assess your understanding. Can a moving object be in equilibrium? 1.71. It can if it has constant velocity. Yes, if velocity is constant. 2. If you have an object 3 times as heavy as you can lift, how could a lever be used to lift the object? Where would the fulcrum need to be placed? So, three times the object, I would guess that the fulcrum needs to be placed. So, like, this was 4 times the object and a quarter of the distance. So, yeah, 3 times the object, 3 times the distance. So, 3 times the distance means a quarter of the way. So, if this is the heavy object, so this is you, and this is 3 times you, then the fulcrum, your distance to the fulcrum needs to be 3 times, or I should have done this the other way around. The fulcrum should be, I guess, a quarter of the way away from the object, because this is 3 times this. So the distance should be 3/4 distance. All right. Conclusion. We made it. In this chapter, we've equipped you with math, the language of physics necessary to understand our first important topic, chemical and physical foundations. We learned kinematics, Newtonian mechanics. We learned displacement, distance traveled, velocity, speed, acceleration. We understand constant acceleration. If the vector sum of all the forces acting on an object is equal to 0, the forces cancel out, and the object experiences no acceleration, condition known as equilibrium. The first law, even when objects aren't touching, they can still exert forces between them, like gravity. Linear motion and projectile motion, inclined plane, circular motion. We also consider the special conditions of translational and equilibrium, translational and rotational equilibrium. All right. So we learned SI units, vectors, scalars, the dot product, the cross product, how to add and subtract, how to multiply, displacement, distance, velocity, friction, static and kinetic, coefficient of friction. We learned what acceleration was. We learned Newton's laws. We learned about linear motion, projectile motion, inclined plane, circular motion, free body diagrams, translational equilibrium, rotational equilibrium. We could go through the answers first, before doing more practice, let's go through the answers for the problems that we've already done. (1.1). Do we even remember what the things are? Oh, so I put this in terms of kilograms. What we were supposed to do was put it in terms of the slug. So in this case, a slug is pounds times seconds squared. So basically, if you want to take feet out of this, this is what a slug is. So if we take, multiply, so a pound is a slug foot per second squared. That's what they're trying to get at. Next one, angstroms, centimeters, inches, foot, mile. You do good on that. 1.2, vector addition, unlike vector multiplication, is a commutative function. The resultant a plus b is the same as b plus a, so there would be no difference between the two results. Oh, I got this wrong. No difference. Two, we got right. It'll be in the opposite direction. 3, a scalar is calculated from two vectors by using the dot product. Scalar dot product. A vector is calculated by using the cross product. We did that right. Scalar dot product, vector cross product. Number 4, I said false. I don't even remember the question. Maybe we should do these as we go through them next time. Yeah. The resultant vector comes out of the page. We got one of these wrong here. Let's go down to 1.3. Instantaneous speed is the magnitude of the instantaneous velocity. Yay. Average speed and average velocity must be unrelated because speed does not depend on displacement, but is rather total distance traveled divided by time. So also we got that right, that they are not, that average speed is not the magnitude of average velocity. Number 2, true. Number 3, velocity is the rate of change of an object. Displacement is a function of velocity acting over a period of time. So we kind of got that right. V is d over t. D, displacement is a function of velocity acting over a period of time. D equals vt. Looks pretty good. I guess I should have deltas in there. Should be a delta, whatever. 1.4. Direction of the friction force always opposes movement. Once the instantaneous vector, velocity vector is known, or net force in the case of static friction, the friction force must be in the opposite direction. So not just that it's perpendicular to the surface, but specifically friction is going to go in the opposite direction of motion. of velocity. The direction of friction is the opposite of the direction of velocity. Number 2 is if there's no net force acting on it, velocity will be constant. 3, false. 4, gravity, electrostatic, magnetic, elastic. 1.5. 1. In the absence of any forces, or when the net force is 0, there will be no change in velocity. Object at rest, no force, no acceleration. Pretty good. Acceleration results from the sum of the force vectors, F equals ma. All forces acting on one object have an equal and opposing force acting on the other object. So if A is acting on B, B is acting on A. 1.6. The only force acting in both free fall and projectile motion is gravity. So that's kind of saying that the y component is the same because that's gravity. Product of sine and cosine is maximized when the angle is 45 degrees because horizontal displacement relies on both measurements. The maximum horizontal displacement will also be achieved at this angle. Vertical displacement will always be 0 as the object returns to the starting point. Objects launched vertically will experience the greatest vertical distance. So for displacement, it's negligible. But for distance, if you just shoot something straight up, that's going to be the longest distance traveled. If the equation for centripetal force is F equals mv squared over r, and force is simply mass times acceleration, then acceleration equals v squared over r. Good job. 1.7. A moving object can be in either translational or rotational equilibrium or both. Translational equilibrium only requires the net force of an object be 0. Its velocity is constant. The corresponding condition in rotational equilibrium is that net torque equals 0. Its angular velocity is constant. So yes, as long as velocity is constant. One could place a fulcrum 1/4 of the way across the lever, closer to the object. The ratio of the lever arms would then be 3:1. Which means that only 1/3 of the original force is necessary. Yay! All right. 15 problems. Multiple choice, but there might be some calculation involved. Let's see if we can get through these real quick. Number 1. A man walks 30 miles east, then 40 miles north. What is the difference between his travel distance and his displacement? Travel distance is 30 and then 40, whereas this distance is 50. So distance is 70, while displacement is 50. Oh, so the difference between the two is 20. So the answer is B. All right, 2. 1,000 kg rocket ship traveling 100 meters per second is acted on by 20 kilonewtons in the direction of its motion for 8 seconds. What is the change in velocity of the rocket? Change in velocity is going to be acceleration applied over time. It doesn't matter what its starting speed is. Force, 20, equals mass times acceleration. So that's what we're looking for, A. So, but this is kilonewtons. So this is 20,000 newtons. Also, kg, kg is good. All right, so this divided by 1,000. 1, 2, 3. So this will equal 20 meters per second. So that force causes an acceleration of 20 meters per second up. All right, we're just going to leave it as 20. And then the change in speed is going to be 20 times 8. Did that do it? (160 meters per second). I'm going to go with A. All right. Number 3. A car traveling at 40 kilometers per hour. And the driver puts on the brakes, bringing the car to rest in a time of 6 seconds. Takes 6 seconds to stop. What is the magnitude of the average acceleration of the car? Magnitude of the average acceleration. So 40 kilometers per hour. So I guess we could keep it in kilometers per hour because all the answers are, we don't have to turn it into meters per second. So if he's going 40, takes 6 seconds to stop. The magnitude of the average acceleration. In the beginning, it's going 40 miles an hour, 40 kilos an hour, but it's not accelerating. And then it starts decelerating for 6 seconds until it stops. So how much deceleration does it take to stop? I don't know the weight of the car or anything. So I'm just going to say 40 times 6 because those are the only two numbers we have. $240. Let's go with A. An elevator is designed to carry a maximum weight of 9,800 newtons and to move upward at a speed of 5 meters per second after an initial period of acceleration. What is the relationship between the maximum tension of the elevator cable and the maximum weight of the elevator when the elevator is accelerating upwards? So it says move upward at 5 meters per second. That's a speed after an initial period of acceleration. We don't know what that acceleration is. How long does it take to get to 5? What is the relationship between the maximum tension in the cable and the maximum weight of the elevator while the elevator is accelerating upwards? So if it carries 9,800 newtons of weight, that will increase during the acceleration. So the tension is greater. Has to be greater. I'm just going to go with A. Less than doesn't make sense because then the elevator would fall. I'm going to go with A, greater than. At a place where g equals 9.8, an object is thrown vertically downward with a speed of 5, while a different object is thrown vertically upward with a speed of 10. Which object undergoes a greater change in speed in a time of 2 seconds? The change of speed should be